All right, here we go. We're going to work out the next section of problems on activity 115. So this says a compound gear train is composed of 4 gears, A, B, C, and D. Gear A has 10, is meshed with B. B has 20 and shares a shaft with gear C. All right, so we've got B and C sharing an axle or a shaft. So let's start kind of drawing this out. But we've got 10, 20, and then 16 for C, and they don't tell us for D probably. Okay. So 10, 20, and 16. So let's go to our camera and let's draw this. This is number 5. So we're going to have gear A with 10 teeth. That meshes with gear B. With 20, and then on the same axle it's probably not great that I did it that way. We've got gear C, and I think it was 16, right? Yep, 16. Let's see, I'm trying to get, okay. And then you've got gear D with an unknown number of teeth. Okay, so there's us sketching and kind of annotating. Okay. Power is supplied at gear A with 100 foot-pounds of torque and is traveling at 1600 RPMs. So those are going to be constant through this problem. So let's go ahead and kind of annotate for A that the torque at A was 100 foot-pounds and the angular velocity at A was 1600 RPMs. All right, number 6. It says the necessary torque output for the entire system is 500 foot-pounds. What should the gear ratio of the system be? So they're not asking us to find the gear ratio. They're actually, they are. They're asking us what the gear ratio is, but based on the torque being 500 foot-pounds. So we want the torque at D to be 500 foot-pounds. And the question is, what is the gear ratio? Okay. So here's the deal. When calculating gear ratio, our formulas for a compound gear train like this, if I write our formulas up here. So gear ratio is equal to the torque of the output divided by the torque of the input, period. If you know those actual characteristics, if you can get that ratio, you have the gear ratio. However that translates through the gear chain, right? If we've got this much output torque and we put that much in, that should summarize what the gear ratio is. Similarly, if instead of knowing the torques, you knew the angular velocities, whatever happened through this gear train, kind of the very initial RPMs or angular velocity of the input gear, and knowing what the final output gear, what its RPMs are, the ratio of those should summarize the total gear ratio. So we could also say the angular velocity, now this is input over output with angular velocity, but that would work. You would not need to go through and calculate smaller gear ratios for where all the teeth mesh. However, if you were going to calculate the gear ratio using the teeth or diameters, all right, then you have to find the gear ratios of where those teeth actually mesh. So we would have, so for teeth or diameter, I'll do N for teeth, we would have a gear ratio from A to B, so it'd be out over in, B over A. A is driving B, so B is the output, A is the input. We do not have a gear ratio from B to C. the teeth don't mesh, they share a shaft or an axle. And then we do have a gear ratio from C to D, where C is driving D. So D is the output, C is the input. And then we have to find the product of those. Now, unlike a simple gear train, there are no common factors that cancel out to give us kind of this gear ratio of just the number of teeth on the output over the number of teeth at the input. So this is actually our formula. We would, for this gear train, this is what our formula would be. We'd have to multiply those two gear ratios together. Now, whether we calculate gear ratio using this method, or this method, if it's the same gear train, the gear ratio should always be the same. Okay, so for number 6, because they have supplied us with the input torque and given us the output torque at D, we can use the ratio of the torques to know the gear ratio. So we're going to say that gear ratio is equal to the output torque over the input torque. The output torque is 500 foot-pounds. The input torque was a constant 100 for this set of problems. The units cancel out, just so you know, with gear ratio, and we're left with a ratio of 5 to 1. All right, number 7. With a system torque output of 500 foot-pounds, how many teeth should gear D have? So, with the same output torque, 500 foot-pounds, okay, we know that we have a gear ratio of 5 to 1, correct? The question is, what is the number of teeth that gear D needs to have to make that happen? Since we're looking for a number of teeth, we've got to use a formula that actually has that in it. So we're going to use this expression. All right, so we're going to say the gear ratio is equal to the number of teeth on B divided by the number of teeth on A times the number of teeth on D divided by the number of teeth on C. We know everything except for the number of teeth on D. We've already determined that the gear ratio with this 500 foot-pounds of torque is 5 to 1. I'm going to write it as a fraction, 5 over 1. The number of teeth on B was 20. The number of teeth on A was 10. The number of teeth on D is unknown. And the number of teeth on gear C was 16. Now, the first thing I'm going to do is go ahead and reduce the 20 over 10, make that a simpler fraction. 20 over 10 is 2 over 1. All right, and I really don't have to write these ratios of 1 if I don't want. So maybe I'll just now write 5 equals 2 times ND over 16. And I need to kind of work on getting rid of the 2 and the 16. There's obviously just different ways to do it. One way is I can reduce. Right, this is really like one big fraction, so 2 and 16 can reduce to 1/8, and I get ND over 8 is equal to 5. And then the very last thing is to cancel out that factor that's dividing 8, and I can do that by multiplying both sides of my equation by the same factor, 8, and that will cancel out that factor of 8 up from the bottom, and I will have my solution. The number of teeth on gear D is equal to the product of 8 and 5, which is 40. And so my answer should be 40 teeth on gear